Hello everyone, my name is Zuho from Automatic Control Division, LINK-SIC University. So today I'm gonna talk a little bit on about my current work. Is the main goal of this work is we want to detect a system change happen in the quadcopter where we do have sensor bias and GWIN. So the motivation is usually quadcopter needs to operate in a closed loop because it's an unstable system, and usually it's also perform some mission outdoor where wind become critical, and the problem become really challenging when we do have the sensor bias and wind, and we want to estimate or detect a change in the payload. So to do it, I need to perform the quadcopter in the simulation and in the experiment. For the real test, we design a path for quadcopter consists of two parts. The first is nominal, is like for a mission where a quadcopter can fly from point A to point B, and for additional excitation where mainly for estimation and detection. So one question you can have is why don't we uh, uh, put every unknown into a state space vector, and basically we can use, for instance, nonlinear estimator, extended Kalman filter to estimate the unknowns. But unfortunately, we show in this work that the extended Kalman filter doesn't work really well, mainly because we have the closed loop effects and imperfect noise modeling. So in order to overcome this limitation, we propose two-step approach when we first estimate the sensor bias. Then secondly, we estimate or we detect a system change. For the first step, we use a navigation model taking the IMU input as our IMU measurement as an input, and we have GPS as output. You can see in the next picture that the estimated sensor bias follow really well the true sensor bias. And for the second step, we reuse the IMU data with when we did remove the sensor bias, apply for a sensor to sensor model, and the indication or the cost value we consider here is the instrumental variable cost values and computed by equation 4. In the next plot, you can see that we have significantly improvement in the IV code function if we remove the sensor bias on the right subplot. Like we just see clear change in the level where the mass increased roughly from 0.5 to 0.6 around 70 seconds. And of course, in detection, we need to evaluate the detection performance. And to do it, we propose the detection rate, and we consider average time to detection. And basically in this, we design 3 different flight tests. The first flight test A, where we have small excitation through small v, and we have the small r as the yaw rate. So you can see from the navigation model 2, we have the yaw rate as a parameter here, and in the sensor to sensor model, we don't consider the yaw rate. So the yaw rate considered as process noise in sensor to sensor model. And similarly, we have fly B, fly C, and you can see in the next table that fly C gives the best results because we have enough excitation and we have small enough yaw rate. So the whole approach here and the results formulated as a paper, and we submitted it to Robotic and Automation Letter 2021. Thank you for your attention, and bye-bye.